And now, for a panel about quantum defense, I'd like to invite Mr. Dror Ofer, Head of EPQ Division, Science and Technology Unit at MAFAT. Thank you.
Can you hear me? I'd like to invite my fellow panelists, Inbar Badian, Head of Strategy Group Manager at the CTO Office of Microsoft, and also founder and head of the Microsoft Quantum SAFE program. And then Amit Ben Kish, co-founder of Quantum Art, a leading Israeli startup in quantum computing, formerly at Rafael, leading various research groups, last position as division CTO, leading 1,300 employees in various quantum-based projects. And then finally, Nir Davidson, Professor of Quantum Physics at the Physics of Complex Systems Weizmann Institute, also Chair of the Scientific Council, aka Senate at Weizmann, and Head of the Crown Photonics Center at Weizmann. Thank you. Can we start the presentation, please? I'd like to say a few words about quantum technology, and then we'll start our discussions. Still waiting? Okay. Next slide, please. Okay, so quantum mechanics is, next slide, please. Quantum mechanics is the physics of very small systems. And in spite of dealing with small systems, it has very big implications in our everyday life. But another thing that can be said about quantum mechanics is that it's strange, in that it very often contradicts our everyday experience and intuition. Next slide, please. Okay. The first example is what is its namesake, quantization of energy levels or states, in the sense that, a simple analogy would be that I can place my phone 1 meter above the ground and I can place it 2 meters above the ground, but there's no way I can place it in the middle. Okay, and that basic physics prohibits that, strict impossibility. Next slide, please. Many of our existing technologies are based on this very simple principle. This is the first generation of quantum applications. Things like the transistor. The smartphone contains about 1 trillion of them. Or the LED, light-emitting diode, the basis for the display on this same smartphone, and the laser, just to name a few. Next slide. But there are other weird characteristics of this technology, and we're now beginning to exploit those too. Things like entanglement, which I won't describe right now, or next slide, please. Superposition, which basically says that a system can be in 2 places or 2 states at once. This was made famous by the story of Schrodinger's cat, where a cat in an enclosed box is both alive and dead at the same time. This certainly is weird and raises a lot of philosophical questions, but the fact is that this is exactly how the world works, and the proof is not just scientific proof, we have applications. So next slide. The new breed or the new crop of quantum technologies can be divided into 3 main areas or vectors. The first is quantum computing, the most well-known but also the least mature of the 3. We don't yet have quantum computers that actually do useful work. Then there's quantum communication, and specifically cryptography. I'll say just a few words about that in a minute. And finally, quantum sensing, the ability to measure various physical quantities at exquisite accuracy. Next slide, please. So for instance, if you're talking about a quantum computer, everyone has a sense that it's fast. But it's more than that. The real issue isn't that it's fast, it's that the scaling of the speed is exponential in the size of the system. So if you have, say, a computer with 1,000 units, and you add just 1 more computational unit, you've doubled the speed of the system. You add 50 more units, and you have a factor of 10 to the 15 speed up, which happens to be everything we've experienced in digital computing since the first computers were introduced in Los Alamos back in the 1940s, all the way up to the fastest computer in existence today. roughly 15 orders of magnitude. And here you get it by increasing the size of your machine by just 5%. That's the reason people are excited. Now, people have known this for many years, but what really got them excited was when in the previous slide, that in 1994, a mathematician named Peter Shor came up with an actual algorithm that is both useful and makes use of this exponential power. It deals with the so-called factoring problem. Again, I won't go into it, just to say that it is central in most commonly used encryption methods, such as RSA and Diffie-Hellman. And if and when we have quantum computers powerful enough, then we need to find a new way to encrypt our messages. The old way won't be effective anymore. Next slide. Then comes quantum communication, and I'll just focus on the left side, the quantum key distribution. Since quantum computers killed our old encryption method, quantum mechanics offers us a new way of doing it, of exchanging keys between two sides without anyone being able to eavesdrop, or more accurately, if anyone eavesdrops, the sides will know about it. And again, the details don't matter. Doesn't matter how you eavesdrop. Quantum physics says it will be known. There's no way of doing it without sending a clear signal. Next slide. And then finally comes quantum sensing, which is, like I said, measuring things very accurately, like for instance time, an error of 1 second, say over the entire life of the universe. Measuring acceleration, gravity, electric and magnetic fields, and things of this nature, which opens up a lot of possibilities and a lot of applications, such as, for instance, navigation in the absence of GPS. I'll go over this very quickly. Next slide. There's just a lot of applications. No point, I think I've used up most of my time, right? So I'll just end it here. The point is that we're undergoing a major revolution in a number of technological areas, and now we're here to discuss those among the panel. Thank you. So, my first question to each and every one of you is, when can we expect quantum computing to start solving real-world, worthwhile problems? And what do you project that problem, that first problem, is going to be? Second, what do you expect the impact with positive and negative, both positive and negative, of quantum systems is going to be on our society? And point out possible problems or issues that you think need to be addressed. Neil. Okay,
so I don't know the answer to the first question, but I do want to stress that in the last maybe 5 years, we have undergone 2 amazing revolutions already in the field of quantum computing. The first one around 2019-20 is quantum supremacy, where Google announced, and later other people showed, that a quantum computer can take a non-useful problem, which is suited to it, and calculate it a bit faster than a regular computer. Now we are 10 orders faster. So that's done. And the second revolution is happening now. For example, yesterday Google announced, and this is quantum error correction. And this is really a breakthrough, because when we use quantum error correction, we are overcoming the main difficulty of quantum computers, which they have errors. So with these 2 revolutions undergoing, I think people like myself feel quite confident to predict that in about 10 years, we will have a useful quantum computer that can solve real-world problems.
But you're not betting what it's going to be.
That's another good question. I think we all agree, and you also mentioned that, breaking codes. So breaking codes, first we have less competition from AI, because AI gives sort of rough answers. And this is not good enough to breaking codes. You can calculate many other things. So if a quantum computer can indeed scale up exponentially, it can break codes. This will be very good for some people. It will be very bad for other people, but it will definitely change the world. We'll hear in a moment what Microsoft wants to do about that. There are many other applications, probably starting from the scientific applications, material science, new medicine. So all these things involve a lot of calculation, because physics in the end is a quantum computer, because it involves many particles interacting in a quantum way. So it's natural for the quantum computer first to address that. And then there is a lot of optimization problem coming from the heuristic world, which may be addressed, but nobody really knows yet.
So may I also take that? So for some reasons, I agree with Nir, with all the things you've just mentioned. I think one thing I would like to mention that quantum computing is, first, it's here to stay. I think for many years it was like just theory and small setups that show, first principles, but now it's not only in the academia, it's in the industry, and there is a lot of investments that help scale up the system. And I think that the major thing here is the scale up, whether you will be able to have your quantum computer work at scale, and this also relates to the fact that you were able to do error correction. So now that we know that there are some examples that already show error correction, then the scalability, I think it's sort of I would say, an engineering effort. We always say that the qubits know their work. It's only us that makes them malfunction. So we have to be prepared and make them work. And at least at Quantum Art and other companies, we're working very hard on a very on a scale-up strategy that can take us to large numbers. And I would say that I would like to take two time frames. One is breaking RSA codes, which is kind of hard. It's a very large circuit that will take a few years, maybe a decade. But I would say that other things that might come earlier are interesting as well. I would aim for material science, and then it would be batteries and maybe pharmacy and other stuff. It can be optimization problems that are related to transportation and finance. So many of these may come earlier, and I would say within the 2 to 3 years, I would think that first example would show up. And I think that it's a disruptive technology by all means. And I think that it's even hard to predict what we will get when these powerful resources will be available.
I want to add on top of that, from the Microsoft perspective, and I think that the ecosystem will all agree that basically from a cryptography perspective, we have the time frame of 5 to 10 years until we can actually say that the cryptanalysis set of problems will become relevant, or any real-world application that we can use on a quantum machine. But with the progress that we see lately, with all the announcements around us, we can expect that the timeline to achieve applicability will be even shorter than that. So this is one thing. And the second thing that I want to add is that at Microsoft, we divide the development of quantum machines into 3 main levels. Level 1 is the foundational level, the physical qubits and the NIST computers that we have today. Level 2 focused on resiliency with logical qubits, tens of logical qubits, which will allow us eventually to perform some valuable operations. And then the holy grail is to achieve the scalability, which is level 3 with thousands of logical qubits. And recently, we actually announced the collaboration that we have with Quantinuum, that we doubled the number of logical qubits from 12 to 24 logical qubits in only 6 months, and even demonstrated an end-to-end chemistry workflow on one of Quantinuum's system, the H2 system. So we already see today some of the applications of quantum machines coming into reality today. But with that, I want to say that when we consider the applicability of quantum machines, we usually see the benefits for problems that seek to and model the nature, scientific problems. So we mentioned chemistry, biology, material science, and so on. And we also understand that eventually we need to consider, if we want to gain all those benefits, we need to consider all the risks that quantum will bring to our lives, either to the classical infrastructure that we have today from the cryptography perspective. So we discussed the cryptanalysis set of problems, public key cryptography. This is something that we need to start and handle already today, and I believe that we'll talk about it soon. And also from the quantum perspective, we need to think about the dual use. If we talk about chemistry, we can compare that to the dynamite and to think about the bad and the good consequences of this technology and its application, so how we avoid that. and also who can use the quantum machine for which applications. So this is another thing that we need to consider already today if we want to achieve the benefits of quantum.
Thank you. My next question is, can you describe for our audience the investment landscape? How committed are governments and private money to this technology?
So maybe I'll start with Israel and then go worldwide. So in Israel, there's many startup companies in the last 5 years. I'm sure you heard about them. And they actually get money from the private sector, from venture capital. There is still a significant government investment, either from MAFAT, from the security, or from Rashut LeChadshanut. And there's a quantum program that you may know. It was started about 5 years ago. It's going to end soon. We hope to extend it for another 5 years. That was around 1.2 billion shekels. That's about medium size worldwide if you compare it to per capita, and we hope to do a little bit better. And I think government investment is still needed in the next 5 years or so, but we'll see more and more private investment, startup companies, the universities invest a lot of money because somehow quantum computing, even beyond the application, is a good meeting point for many disciplines. Originally inside physics, many different platforms now speak the same language, and recently we have the computer scientists joining, so now they are taking us really seriously, and this is making a huge impact on the field because they really know how to do error corrections and how to find applications. So I think both scientifically in terms of application and growing of the ecosystem, and maybe I want to add something else, that we start to see barriers rising between nations. So if we think about Israelis, we want to make sure that we have an Israeli ecosystem that will not be shut down by barriers that export license and things like that. So this is about Israel, maybe worldwide I will leave to my colleagues to describe.
So I'll start with the Israel and thank the IAI, the Israeli Innovation Authority, and I guess the IMOD that will start soon investing in quantum. I think that's an important benefit, and we can see that its impacts. Nevertheless, I think still most of the investment comes from the private sector. But that, I think the fact that the governments do invest in quantum makes a difference. They always ask, are you there? Are the agencies are there? And that makes a huge impact. As you all know here, the synergy between public and governmental money is important. It's important in defense, but it's important here. And thanks for the agencies that help us here. And worldwide, I would like to mention that the investments are huge. They are like, I would say, orders of magnitude more. I would say that you can see worldwide, the people are talking about tens of billions of dollars. And just see how much of investment the Chinese invest in quantum. I think it's like $15 billion. And I would like to say that both Europe and the US invest at least similar or more. There are a lot of investments alongside with the private sectors, and most of the countries invest like hundreds of millions of dollars into these quantum companies. And I think the reason behind this, as mentioned before, is that it's really a disruptive technology, and government sees this as part of the national security agenda. And I do agree with Nir that barriers will come. Now we are friends with the academic colleagues, and we share information. Everything is happy and fine. But I think barriers will come. And I would say that I would look at this as a club, and you would want to be in this club at the right time. Otherwise, you will use your ticket. So it's important to be there now in order to be part of this club and then grow with the other ecosystem worldwide.
I couldn't agree more. I think that we see governments globally stand up their own national and regional quantum programs to advance the development of both the hardware side, quantum communication, quantum networks, and also quantum software. And we also see the private sector and multinationals invest tons of money in the development of quantum machines, understanding the risks in collaborations with either startups, partners, the academia, and of course with the society to understand what we can do to not just develop the machine, but also what will be the usage of that machine. So we see the investment. I want to say that it's not just from the development side. We also see it coming. The investment, the money investment goes to the understanding of what will be eventually the quantum, the responsible computing approach that we will take for those machines. First of all, if we want to use this technology, we need to understand what will be the controls that we want to put on that, starting from the impact on the classical infrastructure as we discussed, the impact on cryptography, what's going to be the new algorithms, the post-quantum cryptography algorithms that we're going to standardize, which is something that will take years if we think about all the areas that we will need to replace the cryptography that we have today and then to maintain it, all the way to the usage of those machines and who can use this, who can use that machine, what's the collaborations that we can agree on that, and we can take examples from the responsible AI approach that we have today and controls that we have today. So it's going to be similar to what we will need to develop for quantum. Also, we will need to understand how everyone will be able to benefit from quantum machines and not just privileged few. And to make sure that we define the access to those machines and the hybrid usage of quantum machines with the high performance computing and AI that we have today. We at Microsoft don't see the quantum computers as something that will exist in isolation. It will exist in a hybrid environment with classical computers, AI, and the system that we have today. So it's also something that we invest money today to understand how we define the boundaries and the regulations on this.
I'd like to add just a few words from the perspective of the Ministry of Defense. The unit that I work for, the Science and Technology Unit, which focuses on early stage science and technology project where actual feasibility is still in question. Our investment in quantum technologies, not just computers, all three branches that I spoke of earlier, is by far our largest investment in any technology in any field. Now, they spoke about the Israel National Initiative in Quantum Technologies. My boss is head of that initiative. It's a cooperation among several government ministries and other authorities. But we recognize this both as a national issue and a security issue, both economically and militarily. This is clearly a dual-use technology, and for us, not being in the game simply isn't an option. Next question. We focused on quantum computing so far. I'd like to say a few words about other quantum-based technologies. If you had to guess, what do you think 5 or 10 years from now, what are the most impactful technologies that we are going to see? What exactly are they going to do for us? Neil.
Okay, so I think we all agree that quantum computers are the exciting revolution of tomorrow, hopefully. But quantum sensing, I would like to focus on quantum sensing, is happening today. And I think it's penetrating more than people here would imagine, starting from very exotic places to routers that can synchronize with atomic clocks. So I think it's already having a significant impact. And I also want to stress that it's sort of building our tools and our trust in the quantum world, because we are doing things today and there's a very deep connection between the sensing part and the computing part. Many of the techniques, how to keep the qubit alive, how to control it, how to use error correction to improve computing tomorrow, we're already applying them today on quantum sensing. So beyond its important application, I think it's really pushing the quantum tools into technology and into the industry. And I see a lot of applications already happening, and that will definitely grow in the next 5 years. And you already mentioned navigation. I think these quantum sensors are becoming now miniaturized, so they are small, and they are becoming cheap. So we'll see them more and more in navigation and timekeeping definitely, and the sensing of fields, magnetic fields, electric fields. So there's really a lot of applications for quantum sensing, and this is maybe not going, we'll not see any exponential growth, but we'll definitely see a steady and a very strong growth in improving the ability to sense small forces. And of course, in physics, we are very much excited of using quantum sensors to do new physics that will then come back to you as new applications.
So you think that navigation is where we're going to see the most impact?
Probably, yes.
I just want to mention that I would like to proudly mention my colleagues in my previous work at Rafael, where they have this Center of Excellence that is working with the IMOD, and they already provided sensors that can make a difference in terms of magnetic field, navigation, gravity sensors, and more advanced measurements. All of them are now, so the accuracy are like at the state of the art, and they are also already in the phase of deployment sensors, and they are fielded as part of systems. That's a process they will have to encounter, but definitely sensors are already there, and it will influence autonomous navigation and other means that are important both for the industry and for the defense sector. On the other hand, I would like to mention that quantum computer, for the quantum computer, I think they will also revolutionize the system. So you can think about an iron dome system that you have to calculate many trajectories. If you can do it much faster and more efficient, it means that you can have like a better system. And that's just one example. I would say that in every piece of, or any project that you will have to, you can deal with more energetic materials. You could think about other sophisticated optimization algorithms. And whenever you use them, you can get significant upgrades in your performance. So I think both will do the difference. First, the quantum sensors, they're here, and then the quantum computers that I think will follow and make the progress.
I want to stress the impact that we're going to see on science. Again, chemistry, biology, and everything that relates to material sciences. I believe personally, and we see that as part of Microsoft, that we're going to see huge impact on those fields, and especially the connection that we're going to see between quantum machines, the classical computers, and AI. It's going to revolutionize those fields, so it's exciting to think about it. But if we think about what we have today, we do see the progress on quantum cryptography that is going to evolve in the upcoming years. We already see it evolving today, other than the technologies that were just mentioned. So quantum applications, quantum algorithms, and quantum cryptography will be also something that we expect to see growing in the upcoming years. And I also want to stress the importance of the growth for those fields to make sure that, again, we will be able to safely use quantum machines as soon as they are available, and to make sure that we don't use them for harming the classical infrastructure that we have today or other dual usage.
Just a personal note for me, if I have to look at all the applications that perhaps will be affected by quantum computing, I have to name chemistry as number one. If you know anything about the pharmaceutical industry, for instance, you know that it's basically trial and error, very little design in the scientific or technological sense. In fact, the process of bringing new drugs into this world is called drug discovery and not drug invention for a reason. Most drugs were not invented by human beings. Famous example is penicillin. It was invented by fungi, not human beings. And we just adopted it. And that's the way it's going even today. The ability to actually design / predict chemical processes doesn't exist today. And when it does, if it ever exists, then that will really change the world. But it's still very far way off. And by the way, it's not entirely clear if quantum computers will even be able to do this. It remains to be seen. It's an open question, although I'm optimistic. My final question, Quantum computing, a full-stack quantum computer consists of several levels. There's the inner core, then there's the error correction, and then there's the algorithms, the compilers, whatever, enabling human beings to translate their ideas into something that a quantum computer can actually execute. Can you say a few words of where Israel is compared to the world in each of these areas?
Maybe I'll refer to the scientific part and I'll leave you to the industry part. So I think in quantum science, Israel is among the world leaders, and I hope it will stay so. There's a huge growth in the interest of Israeli physicists and computer scientists in quantum. I think I can say that quantum computer is the most interesting scientific question that we have now in this decade or two. So we are really attracted to that, and I think that is very important because the academia is responsible for building the human infrastructure. We have to educate quantum physicists more than we have. We have to educate quantum engineers that did not exist until recently. So in that term, I think Israel academia is doing quite well, but should do even much better. And I'll go live.
So when you build a quantum computer, you would like to make what we call the full stack that we're referring to. We're at Quantum Art, we're building a full stack system. But nevertheless, you need all the ingredients, and there is a company, a leading company in each of the layers. So for hardware, we have a few companies that Quantum Art uses trapped ions, but there is another company, like a Quantum Source, that uses photons. There is work on atoms. There is another company, Quantum Transistors, that work on diamonds. And then the next layer would be the electronics that operate the system. And here, there are leading companies like Tabor and Quantum Machines. And then there is a software and error mitigation and layers. There are Kedma and Classic, and I think all of them are already showing performance that leads the industry. You can see their announcements. So I think we're there with all the ingredients of the stack, but we need to push forward fast, and we have to do more collaborations with giants, and then make the thing happen here in Israel.
To add on that, I think that Israel has the power to impact on the security side as well. And this is why we basically founded and leading the Quantum Safe program from the Israeli side all across Microsoft, working with global governments, global customers on this initiative, how to secure the classical infrastructure and how to bring security concepts into the development of quantum. So I think that this is another advantage that we have here in Israel, and also the ability to connect the dots between different governments, different parties that we have here, the academia, the startups, the growing community of startups we have here, and this should be our main priority to understand how we bring more of that to Israel and expand the ecosystem that we already have today, but make sure that it's a leading ecosystem of quantum globally.
Thank you very much. I think our time's up. Thank you all.
Thank you.